to another edition of Cracking the Cryptic. I haven't done a Killer Sudoku for a few weeks now, so I'm going to look at the deadly Killer Sudoku from today's edition of the Times and work through it. These are normally quite interesting puzzles, especially if you enjoy a bit of maths, because they involve arithmetic normally. So just a reminder, the way to solve these puzzles is to focus on the fact that the number 45 is absolutely critical. Why? Well, because the number 45 is what you get if you add all of the numbers from 1 to 9. And there are three different, I suppose, areas in a Killer Sudoku for which this addition is relevant. Every row must add to 45, every column must add to 45, and every one of the 9 3x3 boxes needs to add to 45 too. And we'll see as we solve this that that constraint is extremely powerful when you're trying to get to grips with these harder puzzles. So all I've done at the start, you can see, is I've just filled in some of the cages that are forced with the options that are available. And without further ado, we can write in this number using exactly the principle that sort of outlined at the start of the video. So we've got a cage 13 cage and a 21 cage, so these two cages together sum to 34. So we know that these three cells here must sum up to 11, because we know that overall 3x3 box has to add to 45. Well, if these three cells sum to 11, this cell here has to be a 7, because of we know the whole cage sums to 18, so we can fill in a 7 here. And we can use the same sort of trick on this 3x3 box. So we've got a 24 cage, a 4 cage, that's 28, and this 7, that's 35. So we know these two cells here sum to 10. Now you might say, well, what use is that, Simon? Well, the reason this is useful is because there are only 4 ways of making 10 in 2 cells. We could have 1 and 9, well, that's ruled out by this one. We could have 2 and 8, well, that's ruled out by the 2 over here. We could have 3 and 7, well, that's ruled out by this 7. So in fact, this has to be 4 and 6 in some order, and you can't put a 6 in here, because if we put a 6 in this cell, both of these cells would have to equal 1, which is obviously not valid. So in fact, this is a 4 and this is a 6, which means this is forced to be 1, 3, 1, 3. And these three cells now have to sum to 22, because 28 minus 6 is 22. And there's only one way of doing that without using a 6 again, and that's with 5, 8 and 9. So we can actually write those options in for those three cells. Now, again, this cell now we can isolate the value of, because using our 45 rule, we have an 18 cage plus a 14 cage, that's 32, plus these two cells which sum to 4, so that's 36. So this cell, in fact, has to be a 9 in order to make this whole 3x3 box add up to the right number. Remove the 9 from these two positions. Now, just scanning up column 7, we see this 13 cage. Now, 13 cages in 2 cells can be made in 3 different ways. 6, 7, that's ruled out by this 6. 5, 8, well, that's still possible, so let's write that in. And 4, 9, well, this 9 prevents that option being valid. So again, we've now got, you might not know exactly the order, but 6 of the cells in this column are now sort of identified, if you like. And we're left with 2, 4 and 7 to find. Well, this can't be a 7 because of this 7, so that's only 2 and 4 will be valid here. Put the 2, 4, 7 options into these two cells. Now this 5, 8 is actually more useful than you might expect, because its existence forces this 22 cage in the sense that if this 22 in 3 cells can be made in 2 different ways, we've seen it already. We have a 589 variation and a 679 variation. Well, if this was the 589 variation, this cell couldn't be filled because this has to be a 5 or an 8. So in fact, this has to be 679. I don't know the order again, but often solving these puzzles isn't about knowing the exact order at the start, it's simply eliminating possibilities. So now we've got to fit 3, 5 and 8 are the only numbers left in this 3 by 3 box to place. So this can be a 3 or a 5, it obviously can't be an 8 because then this would have to be a 0, and this can be 3, 5 and 8. If this is 3 and 5, this must be 3 and 5. Okay. There are a few ways I think to make further progress now, but I'm probably going to show you one of the most advanced techniques or advanced bits of arithmetic you'll be asked to do in solving these deadly puzzles. So let's imagine we draw a line down the grid here where the cursor's moving. Hopefully you can see that would split the grid into 2 pieces. And to the right of this line, we know that once the grid is filled, we will have the numbers 1 to 9 exactly 4 times each, because we've got 4 complete columns. So 1 to 9 4 times, well, that's going to sum to 180. But hopefully you can also see that there are a number of, there are only 2 cells that stick out to the left of this line from all of the cages that are contained to the right of it. So only this 34 cage with this cell here and this 7 cage with this cell here stick out. So if I was to add all of the cages up that appear in these 4 columns of the grid, then I know that the difference between this total sum here and 180 has to be the value of these 2 cells. So let's do that and see what we get. So we've got 34 plus 13 is 47, plus 21 is 68. So this gives us 86 with this 18 here, 90, 114, 114, what's that going to be, 122, 142, 150, 157, 175, 189. So I think if we add all of these up we get 189, which is 9 difference from 180. So I know that these 2 cells here have to sum up to 9. And because this cell is already limited, that means that the only options for this particular cell here are 5, 7 and 8. Now often you get lucky and you'd find that this cell would be restricted in some way that really helps. The fact it's part of this enormous 34 cage I think will prove useful later on. But what I advise you to do now is to pause the video and see if you can use exactly that same technique that I've just described, i.e. using, cutting the grid and carving off 4 rows or columns. See if you can spot where to use that in a different place in the grid, because there is another opportunity to do that in this puzzle. Okay, I'm going to show you where. So let's have a look now. Let's imagine we carve the grid up across here this time. So just after the 5th row. And you can hopefully see that this cell is identifiable by the same logic we've just described, i.e. that this time if I add all of the cages up below this line, I'm going to come up with a number that is less than 180 this time, because this cell is sticking in to these 4 rows. And the difference between 180 and the value of all of the cages below this line will be the value of this cell. So let's do that and see what we get. So we get 27, 46, 63, 71, 74, 124, 124, 131, 139, 157, 171, which I think means this has to be a 9. It's always worth, if you're doing this, by the way, yourselves, it's probably worth doing the arithmetic twice, because you get this, you know, if you get this one wrong, you will totally break the puzzle. But I think that's probably right. So let's put the 9 in here and go forward from there. And we can use some Sudoku logic now. So we have a 9 here and a 9 here. So we know that the 9 in this 3x3 box has to appear in column 8. It's in one of these 3 positions, but we can actually rule out 2 of these. If this was a 9, then with this 7 here, we'd have 16 in the cage already, and these 2 cells would both have to be 1, which is impossible. So this is not a 9. We know the 9 is in one of these 2 positions. But let's just scan across and ask ourselves about this 27 cage, 4 cells. Is it possible to make 27 in 4 cells without using a 9? Well, the best we could do would be using an 8, 7, 6 and a 5. And 8, 7, 6 and 5, I think I'm right in saying, add to 26. So that what we can say is there must be a 9 somewhere in this 27 cage, and therefore this cannot be a 9. So in fact, we're able to write the 9 in to this position here. And that immediately allows us to make use of this 7. So if we can't place a 7 in any of these 3 cells, obviously, and none of these 3 cells contain a 7, so one of these 2 cells has to be a 7. Well, this can't be a 7 because there's already a 7 in the cage. So this must be a 7 here. Now we have 16 in this cage, so these 2 cells have to sum up to 5. Now there are 2 ways of making 5 in 2 cells, either 2, 3, 2, 3 or 1, 4, 1, 4. So I'm going to cater for both of those possibilities here. And the reason for just notating that is that you can immediately see, therefore, that there needs to be a 6 in one of these 2 positions. We can write that in like that. And in fact, then whichever variation of the 5 this is will also appear, the other will appear in this 18 box, because we'll have 6 plus 7 is 13, and we need to make another 5 to get up to our 18 total. And we can now work harder on this 27 cage again. So we know it has to contain a 9 from the logic we had earlier. And one question would be, given that we have a 7 now in row 1, is it possible to get to 27 without using an 8? So we'd have to have 9, we can't have 8 or 7, 6, 5 and 4. Well, you can immediately see that you can't get high enough. So we definitely know that one of these 4 cells is also going to be an 8. So we're going to have an 8 and a 9 in this 27 cage. Well, if we have an 8, this can't be an 8. This will have to be a 5. This will have to be an 8. And you can see just by this sort of iterative logic, when we've been able to completely now identify the value of this 27 cage, we know it contains a 9 and an 8, or 9 and 8 add to 17. So the other 2 cells have to sum to 10. But we can't repeat a digit in this cage, so we can't make a 10 with a 1 and a 9, and we can't make a 10 with a 2 and an 8. Now we can't make a 10 with a 3 and a 7 because of this 7. So in fact, the only way that this cage now works is with a 4 and a 6. So this 27 cage is now, we don't know the order, but we know the numbers that will be contained within it. Allows us to remove a 4 from this cell, which allows us to remove a 1 from this cell, because we know these 2 will add up to 5. So you can see now that we've now identified 6 of the numbers in row 1, and the balancing numbers will have to be 1, 2 and 3 in some order, like that. And when you get to this sort of point, again, it's just a case of trying to spot useful bits of arithmetic that you can do. So here now I'm thinking we might have a look at rows 8 and 9 and draw our imaginary line like this where the cursor's moving. And you can see it's less clear. It's not like I'll be able to identify the value of just one cell by doing this. But what I can do is I can identify the value of these 3 cells. Now, ordinarily I might not look to do that, but the fact that these 2 cells are very restricted already makes me think that this is worth doing. So I know that everything below this line will add to 90 this time, 2 lots of 45. So let's sum the cages and see where we get to. So we've got 18 plus 14 is 32, plus 7 is 39, plus 8 is 47, plus 17 is 64, plus 19 is 83, plus 22 is 105. So I know that in order to ensure that everything below this adds to 90, these 3 cells here have to sum to 15, i.e. 105 minus 15 will give us the 90 we need. We can immediately see that if either of these digits is a 9, this is not going to work, because if this is a 9, the lowest number this could be would be a 6. So this would be a 9, this would be a 6, this would have to be a 0. And 0 is not a valid answer in a Killer Sudoku. So in fact, neither of these numbers can be a 9. We can remove 9 from here. This in fact has to be a 9. This is 6 and 7, which is 13. Therefore this has to be a 2. And that should be very, very useful in terms of making further progress with the puzzle. Let's remove a 9 up here. And what have we got? We've got 4, 5 and 8 to place along here. Like that. And we can do more work with this 18 box here. Just looking, because this cell is restricted, it's actually possible to eliminate, I think, 2 of the numbers here very quickly. You can see if this was a 2, then these 2 cells would have to add to 16. Well, that's only possible if they're 7 and 9 in some order, and we already have a 9 in the 3x3 box, so 2 is not possible. Now, I think also 7 isn't possible, because if this was a 7, these 2 cells would have to add to 11. But let's see if that's possible. We already have a 9, so 2, 9 isn't possible for these 2 cells. 3, 8 isn't possible either, because we already have a 3 in the 3x3 box. Moreover, if this was a 7, then we can't have 4, 7 as our way of making 11, otherwise there would be 2 7s in the cage. So that would only leave us with 5, 6. But we already have a 5 in the row. So in fact, if this is a 7, you cannot complete this 18 box in any valid way. Therefore, it has to be a 4. This is a 4, this has to be a 2, and this has to be a 7. And that's really useful, because this 2 here means that, given we already know there's a 6 in this cage, the other number has to be a 3. And therefore 3 isn't possible here, neither is 2. We are able to eliminate this down to a 1, 4 combination up here. Let's remove the 1 from these 2 positions. We can remove the 4 from this position, and let's ask ourselves now, if this is a 4, this has to add to 14 without using 9. The only way that's possible is with 6 and 8. Let's write that in. You can now see that we need to place a 2 somewhere in row 8, but it can't go in either of these positions here because of this 2. So the only place left for a 2 would be here. Let's write that in. That means these 2 cells have to be 1 and 7 in some order, because we still need a 1 and a 7 in row 8 somewhere. and that means that this has to be a 9 in order to make this 19 cage add up to the right number. So we're left here, this has to be 2 and 5 in some order. We don't know yet how that will be made up, but it allows us to remove a 5 over here. You can see that the only numbers left to make up, we still need to place a 6 in this box, so that must be in one of these two positions. And that means that the combination we're looking for here somehow is 3, 8 and 6, which do sum to 17, so that all looks like it's working reasonably well. And we can use a little bit more logic. We've got a 12 box here in 4 cells. Now, it's not normally that useful, but one thing we can say unequivocally is that there must be a 1 somewhere in this cage, because if there isn't, then the lowest total we could make in 4 cells would be 2, 3, 4 and 5, which sum to 14, I think. So we know there's a 1 somewhere in this cage, therefore this can't contain a 1, which resolves this ordering here. You can see this 2 here is actually checking this 2 up here, so that forces this to be a 3 and this to be a 2. And we're probably about ready to have another look at this, this 34 cage. Now you remember we said these two numbers have to sum to 9, so 7 is ruled out here as a possibility because this number can no longer be a 2. Well, we can use a bit more Sudoku logic here. We've got a 1 here, obviously that forces this to be a 1. Forces this to be a 3, that resolves this 3 and 6 combination, that resolves the 6 and 8 combination too, which is all reasonable stuff. So we're left with having to place 2, 5, 8, 8 I think in these 3 open positions in this 3 by 3 box here. And the next thing I can see is we can use this 3, believe it or not, up here, because if we scan down we can see in this box here the 3 has been forced over onto the left hand side. It's in column 4, it's in one of these two positions. So simple Sudoku rules tell us that one of these 3 positions has got to be the 3 in the central 3 by 3 box. Well, it can't be here because this has to be a 1 or a 2. So one of these 2 positions is a 3, and that's useful because this is a 25 cage. That means the other 3 digits need to sum up to 22 again, and we've seen that 22 is a relatively restricted number. Definitely needs to contain a 9, so we immediately are able to write in 9 in one of these 2 positions. And what else can we say about that? Well, the other 2 numbers are going to have to either both be 6 and 7 or both be 5 and 8. I don't think we're quite able to say which of those is ruled out yet. And the other thing we could use here, some people don't like this method, but I think it's totally fair because we know that this has a single solution, this Killer Sudoku. Now, in order for it to have a single solution, there are certain arrangements of digits as we're solving that cannot be possible. So I want us to ask the question, let's imagine this was an 8 here, because it could be a 2, 5 or an 8. So imagine this was an 8, then this would have to be a 2 or a 5. This would be an 8. Let me just show you like this. And let's ask ourselves whether this is possible. And in fact it's not, because look at the arrangements of the 2s and 5s that we get if we end up in this situation. We end up with 2 solutions, because if this was a 2, this would be a 2, this would be a 5, and this would be a 5. Okay, so that's totally valid, and there's nothing that prevents that being a valid solution. Similarly though, if this was a 5 instead, this would be a 5, this would be a 2, and this would be a 2. Again, a second solution that nothing can disprove. There's no there's no arithmetic that would cause either of these solutions not to be valid. So we can say that because of uniqueness, this cannot be an 8. We need to delete that possibility. Now, in fact, if this is not an 8, the only place that can be an 8 now in column 8 is this position. So we can use uniqueness to give us this digit, which is quite an unusual piece of logic, but it should be quite helpful. Okay, and I think that might lead to some more interesting logic. So we still need to place 3, 5, 7, 8 in this row. Let's just write in the possibilities here so I can show you what I'm thinking about. This can't be a 7. So now let's take a look at column 1. In column 1, it should be clear that we can't place an 8 anywhere in this 12 cage because it would immediately break the cage. If this was an 8, you can't make this a valid solution. So there's no 8 in the first 4 positions. There's no 8 here because of this 8 that we've just found. Therefore the 8 is in one of these 2 positions in column 1. Now similarly, we know that in column 6 the 8 is in one of these 2 positions. I don't know which one, but note that these 8s are appearing in identical positions in columns 1 and column 6. Now why does that matter? Well, it matters because if this is the 8, there will be an 8 here, and if this is an 8, there will be an 8 here. But either way, there definitely cannot be any other 8s in rows 6 and 7. So this definitely cannot be an 8 because it'll either be checked by an 8 here or an 8 here. We can remove the 8. Similarly here, we can remove the 8. Similarly here, we can remove the 8. Now, unfortunately, it's not going to, I don't think it's quite going to break the puzzle open. But you can see this is a powerful technique, sort of an X-wing type technique that you might have heard in solving Sudoku context. But solving Killer Sudoku, it comes up more rarely actually. So it's nice to find one here. And this is certainly proving quite a tricky puzzle now, I think. We can see another sort of X-wing pattern of 3s here. I'm wondering if that might be useful in terms of this 21 cage. Let's just fill in the options for the, this could be 5, 8, 5, 8, 5, 8, 5, and the other option was 6, 7, wasn't it, which would be, should have to be this way round with the 7 here. So this 3, 5, 7 is relatively restricted. So we have to ask ourselves, is it possible that this 21 cage doesn't contain a 9? So if it didn't contain a 9, it would also not contain an 8. So it would have to contain 7, 6, 5, 3. 7, 6, 5, 3 adds to 21. That would be the only way of doing it, but that is not valid because we've seen there's an X-wing pattern of 3s here, which means there cannot be a 3 in this 21 cage. So all of that allows us to say there is a 9 somewhere in this 21 cage. Now, is that helpful? Perhaps not. Let's just think quickly about that. Well, it's a little bit helpful. If there is a 9 in this 21 cage, you can see, for example, if the 9 was here, then this cell would have to be a 9, which would mean this could not be a 9. And similarly, if this was the 9, obviously this couldn't be a 9 then, and this would be forced to be a 9. So it allows us to rule out a 9 from this position here, which allows us to state that there is a 9 in one of these two positions. Now, we still need to place a 9 somewhere in this 3x3 cage, therefore. And this 9 here is stopping that from being in row 2. So there has to be a 9 either here or here. Ah, that's interesting though, because it can't be here, can it? Because we've just done a load of logic to show why this couldn't be a 9, and that would rule out a 9 being in this position too. So in fact, all of that allows us to conclude this must be a 9, which was quite a difficult way of getting to that conclusion. And then we can see from Sudoku logic we have a 2 here and a 2 here. We need to place a 2 in one of these 3 cells. Well, that can only go here. Oh, and that's nice because that gives us this 2 and this 5. Allows us to remove a 5 from this position. Okay. And that should now, I think, break the puzzle open, because now let's have a look at the central row of the grid. Fixing this 5 is important. We've got 21 in these 4 cells, and we've got 8 and 5 in these 2 cells. So 6 of the cells in row 5 add up to 34. That means the other 3 cells need to sum up to 11. But if we make this a 7, that would mean, actually that would still be possible, wouldn't it? So 7, this would have to be a 1 then, and this would have to be the 3, because remember we can't put a 3 in this position because of this 3 here. If on the other hand this was a 3, we need these 2 cells then to add to 8, which would be 1, 7, or 3, 5 isn't possible. So we end up with 1, 7 as the only option for this cell here. But that's good enough because we already have a 1 in this 3x3 box from this 3 box. So in fact this forces this to be a 7, which in turn forces this to be a 3, this to be a 3, and this to be a 1. Now, hopefully that will be enough now to break this open. 3, 4, 6, 9 in some order. So the only options now, this needs to be filled with what, a 6 in one of these 2 positions, and the other one will have to be a 1 or a 4. That would mean that would be a 1. This couldn't be a 1, so it would have to be a 4. So this is now the 34 cage is sort of very restricted indeed. Now we can look at the 14 cage here. This is worth looking at because we already have a 1 and a 2 in the column. So let's ask ourselves the simple questions. Does this 14 cage need to contain a 3? Well, if it doesn't contain a 3, the lowest total we could get would be 4, 5 and 6. 4, 5 and 6 adds to 15, so that is invalid. So there is a 3 somewhere in this 14 cage. But look, we already have a 3 here and a 3 here, so the only place left where the 3 could go would be in this top position. Which allows us to, I suppose we can remove a couple more 3s from lower down. We can remove this 3 and this 3. So what are the other 2 digits? The other 2 digits, we're going to have 4 and 7 or 5 and 6. So if it's 4 and 7, it would have to be this way round. If it's 5 and 6, it would have to be this way round. Ah, and there we go. We've got a nice double now. We've got this 4, 6 and this 4, 6. So there is not a 6 in here. Which means that this is a 5, 8, 9 variation of the 22 cage, which which means we can place a 1 into this position, which again ought to be extremely helpful, I'm hoping. Okay, still need to place a 1 somewhere in this cage here, so it has to be in 2 positions now. The fact that there's a 3 in this 3x3 box already means that this 12 has to be 1, 2, 4 and 5. It's the only way of working, because it can't be the 3, 6 variation anymore, which means we can write this in as a 7 and this is a 4, which means this is a 6 and this is a 1, which I think means 22, 26, this has to be an 8. We know these two cells have to sum to 9, so that means it's forced to be a 1 down here. And finally, I think